All right. In this video, we're going to talk about the use of phase change as a means to mitigate the heat generated, or in other words, as a means of heat removal. So we saw when we studied the Monsanto explosion that the main safety feature on the reactor was a rupture disk that was set to burst when the pressure in the reactor reached 700 psi. So this video illustrates how a rupture disk works. And so I'm going to show that video now. Okay, so according to Fogler, the rupture disk in the Monsanto reactor was fitted with a relief valve with a 2-inch orifice that vented to the atmosphere. The maximum flow rate through the relief valve, calculated using fluid dynamics, was hence 830 kilograms per minute. If the rupture disk had worked properly, once it broke, the pressure in the reactor would have dropped, causing the water in the reactor to vaporize. The water vapor would have exited the reactor through the relief valve. So this would have resulted in a large amount of energy removal. So the maximum rate of energy removal, QR, or QR max, due to this process would be QR max is equal to the flow rate of water times the heat of vaporization of water. I don't know why I'm getting these all of a sudden. So if this number here, max value is 830 kilograms per minute, we can get a large flow rate, and then we can look up the heat of vaporization of water. This value here is 540 kilocalorie per kilogram. So if we multiply these two numbers together, we get QR max due to the relief valve is equal to 4.48 times 10 to the 5th kilocalorie per minute. So if you recall the heat generated in removal terms that we calculated when we looked at the Monsanto example, those were on the order of 5,000 kilocalories per minute. So the relief valve is really designed to remove a lot of heat, orders of magnitude more heat than is being generated in the reaction. So if the relief valve works, then it's a very effective heat removal strategy. However, as we know, in that case, it did not work. Now, that's one example of a means of heat removal, and what's happening there is that you get a large flow rate of a species, and simultaneously you are taking that species, the water in that reactor was vaporizing, so as it's doing that, it's absorbing the heat from the reactor, and then it's exiting the reactor, and so you get a heat removal. So there's other ways to do this that maybe are part of normal reactor operation. So for example, one can imagine designing a reactor where, for example, the solvent boils off continuously. Maybe then it's condensed and then it's added back to the reactor. So maybe that looks something like this. We'll just draw a CSTR for the sake of simplicity. So I have, maybe I'll do a simple reaction. We'll do an A goes to B. A goes to B reaction. And then coming out, I have FA and FB. And maybe this is all done in solvent. So this is reaction occurs. So maybe there's some solvent coming in with species A and flowing out with species A and B. Another stream that we might have in this example is the solvent exits the reactor, is condensed, and comes back. So we have some solvent flow rate. Here the solvent is vapor. Here it is liquid. So the heat exchanger is basically condensing that solvent. And if we consider the case where there's no sensible heat changes for that solvent, we can write the energy balance there. So steady state energy balance, we have stuff coming in, FA naught, HA naught, minus stuff coming out, FA, HA, minus FB, HB. And then we need to take into account this circulation of this solvent. So leaving, we have M dot S, and we have HS of the vapor. And then coming back in, we have M dot S, HS of the liquid. So if we look at these last two terms, what we get here, we can say FA naught, HA naught, minus FA, HA, minus FB, HB. These last terms are going to be the heat of vaporization terms. So the heat of the vapor, or the enthalpy of the vapor minus the enthalpy of the liquid is the heat of vaporization. In this case, we have negative of that. So we could say plus M dot S times negative heat of vaporization, where delta H vaporization equals enthalpy of the vapor minus enthalpy of the liquid, and this is all for whatever solvent we have. Here I've assumed this is an adiabatic process. We could add a heat exchanger term on here if we wanted to, or if one existed. Probably a good idea to have a heat exchanger. We could further simplify this energy balance. If we do that, we're going to have FA naught, CPA T naught, what is it, minus FA CPA T plus FA naught X times negative heat of reaction. These are all terms from that we're used to, and then we'd have plus this solvent times negative heat of vaporization of the solvent. So if this was water, this could be, for example, this 540 kilograms or kilocalories per kilogram. And then these terms we know condense into FA naught CPA TO minus T. So this is the sensible heat change of the species A as it comes in. So finally, this gives us where I've basically done all of that in my head, so if I made an error, someone please email me and tell me. Okay, so what we've done here is the heat of vaporization, this third term over here. This provides an additional means of heat removal. So we're essentially boiling off that solvent, we're condensing it elsewhere, bringing it back in. So we're taking out vapor solvent or vaporized solvent, and we're bringing back in condensed solvent. So we're decreasing the amount of enthalpy in that reactor. So another design strategy, so alternatively, one might design a reactor to boil off a product species as a means of distillation. This is called reactive distillation. You can find a short and informative video here. I'm not going to show that, but if you're interested in that, you can click on it. Maybe you looked at that when you took organic chemistry. Another way to incorporate phase change is to introduce a liquid feed to the reactor, which then vaporizes in the reactor due to absorbing the heat generated by the reaction. So we're actually going to look at this in a reactor in class tomorrow. But this is what this might look like. So here you have your reactor, and again I'm going to draw a CSTR for simplicity. Coming into the reactor, you have, we'll just do a simple reaction, FA naught, and let's say that FA naught is a vapor. And then inside the reactor you have A goes to B. Coming out you have FA, FB, but let's say that FA is a liquid. B is probably a liquid too. And let's say that just for the sake of simplicity, let's say that the temperature of the reactor is the saturation temperature, and let's also say that the temperature coming in is the saturation temperature. And that way we don't need to deal with sensible heat changes, although if we did need to deal with them, we know how to do that. All right, so in this example, the energy balance, we're going to kind of do the same thing. We have FA naught, and we're going to remind ourselves that this is a vapor. HA naught minus FA, we're going to remind ourselves that this is a liquid. HA minus FB, HB. And then again, maybe we have a heat exchanger. If so, we're going to add in a UA T minus TA term, TA minus T term, one of those, just making sure we account properly. I'm not going to add that in here, again, to focus on the latent heat part, which is what I want to illustrate here, but of course we could have a heat exchanger. Okay, so now if we go and simplify here, 0 equals FA naught, this is a vapor, HA naught minus FA naught, 1 minus X, that's our FA term, and maybe we'll make ourselves aware here that this is a liquid. This is our FA term. This is a liquid. HA minus FA naught X times HB. So if I go and expand then out these terms, I get FA naught, HA naught. Okay, so here again, I'm going to combine to get my heat of reaction term. I'm going to deal with these terms in just 1 second. But here I have my heat of reaction. I'm going to say plus FA naught X, negative heat of reaction. This takes care of these last two terms involving HA and HB. These two terms at the front, this is where my latent heat now is going to come in. Normally that's where my sensible heat comes in. This is now going to be my latent heat. So the difference between the inlet flow and the outlet flow is that the inlet is a vapor and the outlet is a liquid. What that means is that I'm going to have FA naught, we'll say HA of the vapor, minus FA naught HA of the liquid plus FA naught X times negative delta H of reaction. And for this here, I didn't really leave myself a lot of room here. 0 is going to be equal then. Again, now we have the heat of reaction here, vapor minus liquid. And sorry, the way I meant to draw this actually, this is going to actually add heat. So what I want to do actually is make this I want to switch these around. So what happens is the liquid comes in and it vaporizes. So I'm going to go back and change all my subscripts or superscripts. Okay. So this is where we have the liquid coming in, and once it gets into the reactor, it vaporizes. This is going to give me more what I want. Now I have FA0 times negative heat of vaporization for species A, and plus FA0 X negative heat of reaction. So you see what's happening here is the vaporization of species A is basically counteracting the heat of reaction. So all of the, in this case, we have an adiabatic reactor, all of the heat that's generated is basically going to vaporize the feed. And this, again, acts as a significant source of heat removal. Note that the main difference between this energy balance and what we've been working with is that instead of accounting for the sensible heat changes between the feed and the reactor, we are now accounting for the latent heat change. So this example, our energy balance is 0 equals FA0 negative H of vaporization for species A plus FA0 X times negative heat of reaction. What we've been doing, so in those cases, our energy balance is going to be FA0 CPA TO minus T, so the sensible heat changes. And if we have an adiabatic reactor, we have FA0 X times negative heat of reaction. In this case, in the adiabatic case, for when we have only sensible heat changes, the sensible heat basically has to absorb all that. Sensible heat changes tend to not be as energy intensive, and henceforth, you're not gonna be able to absorb very much heat from that. And so in those cases, we would almost assuredly have a heat exchanger. We should have a heat exchanger either way. Maybe in the former case, or in the latent heat case, it's used as a backup. Whereas in the sensible heat change, it's part of the design. But anyways, this is the difference in using a latent heat versus a sensible heat as part of your heat removal.